Hello and welcome to another walkthrough of AQAA level physics, and today I'm going to do a walkthrough of 748 paper 1, which was conducted in May 2024. So before going into details, please like and subscribe my channel and ask anything if you have any problem in physics. My contact details are mentioned on the left hand side of this video and also in the description. So question number 1. State the names of the four fundamental interactions. So they're quite obvious. One is weak interaction. One is strong interaction. One is electromagnetic interaction. Okay, and the last one is gravitational interaction. All right. State the products of the decay of a free neutron. So it's quite obvious that when a neutron is decayed, it means it's a neutral, so it has to be goes into a proton and a beta, which is electron. Okay, so you can say beta minus, and beta minus is actually kind of an electron. It's actually not electron, it's a beta because it is coming out of nucleus. So electron is a fundamental particle while beta is coming out of the nucleus. So you cannot say that beta is an electron. Electron is a fundamental particle while beta is not fundamental particle. It is coming out of a nucleus. So beta minus, and since it is lepton, so in order to conserve the lepton number, because it has a lepton number of +1, so we need to have antineutrino along with that as well to conserve the lepton number. So it has -1 lepton number, it has +1, so it balanced out, because on the left you have 0 lepton number, and on the right you have to have a 0 lepton number as well. 1.3. Explain which of the following interactions is responsible for the decay of the neutron. So again, it's quite like very easy to understand that a neutron, when decays, it turns into a proton and an electron or a beta minus, right? So whenever beta is or electron is kind of a lepton, and in all the interactions in which you have leptons, they are actually weak interactions. Okay, so what are you going to write? Weak interaction. Okay, and the reason for that, you will write that neutron turns into proton, and this happens because of change in quark. So a down quark is actually converted into up quark. So a neutron is actually having this. This is the structure of neutron, and when it converts into proton, it actually goes like this, U, U, right? So it means a D quark has been turned into a U quark. So which interaction is involved in the neutron decay? Of course, weak interaction, because lepton is there, and then a neutron actually turns into proton and electron because of the change of the flavor of the quark from down to up. Okay, and any interaction in which you have the leptons, it is a weak interaction. You can also write that, no problem. The forces between two moving electrons cause their paths to change. Explain using the concept of exchange particles why the electron paths change. Okay, so electrons are leptons, right? So electrons are leptons, and when they interact, there is a very specific uh, exchange particle associated with electrons, which is called virtual photon. Remember, for example, bosons are associated with baryons, right? And when we have kind of a weak interaction from baryon to beta minus, we have bosons. But for electrons, we have a very specific kind of virtual photons, which are called exchange particles. Electrons are leptons, and when they interact, they exchange their particles called virtual photons. Okay. Now the problem is when the electron is going this way and another electron is coming this way, they have a virtual photon and they have a virtual photon. This virtual photon will be taken up by this electron, and this virtual photon will be taken up by this electron, and as a result, they will go in that way. Okay, so we will say that when electrons interact, they exchange their virtual photons, since because virtual photons are moving in opposite direction. It means they have some momentum. Since virtual photons have momentum, and upon exchange, the momentum of both electrons is also changed. So when the momentum is changed, of course, the direction of the electrons will be changed as well. So the direction of electrons changes, right? Question number 2, a positive pion collides with a neutron and the following interaction is observed. Okay. Sigma neutral is a neutral sigma particle with a strangeness of -1. Remember, it has a strangeness of -1. Identify the classification of each particle in table 1. So you can see pion is obviously a meson, so you will just stick that up, and then neutron is a baryon, right? Then Kuon again is a meson. You will just stick that up. And finally, sigma naught is a hadron with a strangeness of -1. So obviously it is going to be baryon. So finally, what about all these baryons and mesons? They are all hadrons. Okay, don't forget to take this middle column altogether. A conservation rule predicts the following interaction cannot occur. Pion minus plus neutron equals Kuon minus plus sigma neutral. Okay, let's check it out. Why it is not possible to have this interaction? What kind of rules do you have? First of all, law of conservation of baryon number. The second one is law of conservation of charge. The third one is law of conservation of lepton number. And since you can see that it has a meson and a baryon, and mesons and baryons both are hadrons. So whenever you have hadrons in an interaction, it is a strong nuclear interaction. And in strong nuclear interaction, strangeness is also conserved. Not in weak interaction, not in weak interaction. It is not necessary that strangeness is also conserved in weak interaction, but it does in the strong interaction. So we will say, since in strong nuclear interaction, strangeness is also conserved, so I will have another one which is called law of conservation of strangeness. So let's talk about the first one, law of conservation of baryons. It is not a baryon, it is a meson, and it is a baryon. So Kuon is a meson 0 and sigma is a baryon. So you can see that 0 plus 1, 0 plus 1 conserved. Yes. What about law of conservation of charge? There is a minus charge on the left plus 0, and there is a minus charge on the right as well. It is also conserved. What about law of conservation of lepton? On the right hand side, you have 0 leptons, and on the left you have 0 leptons, and on the right you have 0 leptons again. So it is also conserved. So definitely it is going to be a law of conservation of strangeness, because on the left hand side you have pi plus neutron, which both have no strangeness, and there is a quon you have minus and the sigma naught, and it is given in the question that the sigma has the uh, the strangeness of -1, and quon minus is also having a strangeness of -1, so it is actually -2, not conserved, right? So it means they do not follow law of conservation of quants, strangeness, sorry. Okay, now let me explain you about the conservation of the quants. So quants are like 4 types of particles. So quants are like 4 types of particles: k minus k this, k this, and k this. Okay, usually their structure quant plus is always u and this, so it has a strangeness of +1. Okay, but when we do that, it turns like this, so it has a strangeness of -1. Then we have quant neutral. It has like a structure of ds. Okay, so it also has a strangeness of +1. And then you have k naught minus. It has a structure of st, and it has a strangeness of -1. So it's just for your information. Okay, I need to memorize it. Let's move on. 2.3. One way in which neutral pions decay is this. Compare the rest energies of the particles involved in this decay. So you can see on the right hand side, you are getting a positron and electron, right? And for positron and electron, we know that it happens in a pair production. And pair production means when 2 photons coming towards each other, right? When, just hold on. When 2 gamma photons of energy 0.51 each, 0.5 each, they combine, they turn into neutron and, electron and positron. So their rest mass energy is actually equals to 0.51 MeV, 0.51 MeV, okay? And also for this, it's 0.51 MeV. So it's quite 100% sure that the pion is having the energy greater than 1.02 MeV, because it is creating a pair of the antiparticle and particle and some extra energy in the form of photons. So you will say, you can see that one extra photon is created, and there is a pair of particle and an antiparticle is created. So we are saying that pion is turned into a pair production and some gamma, right? So what's the answer to this question? It's very straightforward, that the pion must have energy greater than 1.02, because that is the energy required to create the pair. Okay, so you will write in this interaction, interaction shows creation of particle antiparticle pair. 1.02 MeV required, plus gamma photon, which is also energy, extra energy, okay? Because you need to have some extra energy to create this photon. So this shows Ion 0 has energy greater than, and what energy? Rest energy. Okay, rest mass energy greater than 1.02 MeV. That's it. All right. Point four. The decay of a neutral pion leads to the production of further gamma photons. Explain why. Because it's very, very easy to understand when you created a particle and an antiparticle along with gamma, they can recombine and create two more gammas. Recombine, create two more gammas due to pair annihilation. One thing is called pair production, and the opposite of it is pair annihilation. It means when particle and antiparticle comes close to each other, there is a bang, and they both converted into two photons, which are moving in opposite directions. Okay, so you will have two more gammas. 2.5. The standard model is a theory that classifies elementary particles. Evidence for the theory has been collected since about 1950s. However, the term standard model has only been used since 1973. Suggest why the progress in particle physics is so slow. So it means that you have developed you have some good or enough knowledge of particle physics in 1950s, but up till 1973, you have done a very small amount of work. And what's the reason for that? Of course, you need international collaboration and a lot of funds to do the research. So therefore, the work on that is very slow. 3. Figure 1 shows two prisms A and B of different refractive indices joined to make a block. A ray of monochromatic light is shown entering and then leaving the block. Complete on figure 1 the path of the ray of the light inside the block. Okay, so because this is air and this is prism, so this is quite obvious that for the prism, the light is going to bend towards the normal. So I am going to create a normal first of all here, and then light will be bent towards the normal. Okay. So this is your angle of refraction and this is your angle of incidence. You can see that the angle of incidence is more while the angle of refraction is less. Why? Because the ray is bending towards the normal. Because when light enters from a rare medium or light medium to a denser medium, it bends towards the normal. Okay. And secondly, again here, you have to draw a normal line like this, and then it will go like this. So again, now here, let me change the color. For example, this. Now here you can see that the angle of incidence is this because angle between the incident ray and the normal. And the angle of refraction is again less. So you will say that the prism B is denser than prism A. So what you are going to write? Air to, okay, no problem. In this question, we just wanted to confirm the to complete the figure. And here we need to write for air to prism, you can say that the refractive index of A is more because light is bending towards the north. And for prism A to B, again, because light is bending from towards the normal, I mean, in the B also it is bending towards the normal. So you will just say again, B has more refractive index. Okay. So if you create a diagram in which angle of reflection is more and angle of incidence is less, then you have to write the opposite, because in the mark scheme they have mentioned that both answers are acceptable. You just need to show what you are doing. If you're creating angle of reflection is less and incident is more, you have to write in that way, that the one that I have written. Okay, but if you do the opposite of it, you have to write the opposite of it as well. So both are acceptable. 3.3, describe one non-astronomical application of diffraction grating. So you can see that d sine theta is equals to n lambda. And from here, what you can find? We can find wavelength. This is the formula for diffraction grating, right? We can find wavelength. And the wavelength can help us to identify the wavelength can help us identify various kind of elements or etc in planets and stars. Actually, there are so many uses of it, so you can write just one of them. 3.4. Figure 2 shows a spectrum of light. Two lines in the spectrum are labeled X and Y. Here it is. So the light passes at normal incident through a diffraction grating. The number of lines per meter for the grating is G. The first error diffraction angle of X is at 28.2 to the normal. Calculate G. Okay, for this, you need to zoom in and see where does this fall. So I believe it is going to fall at 350 and this is 375, so 380, 85, 90, 95, 400. So it is falling here. Okay, so it is exactly 380 nanometers to be the wavelength. All right, so when you have the wavelength of 380 nanometers, you have to find the first order diffraction. For example, this is the data n equals 1 for first order. Then you have wavelength 380 into 10 raised to the power minus 9 meters. Then you have theta, which is 28.2 degrees. Okay. And what else you have? Nothing. So you need to find G, which is the number of lines. Okay. Number of lines per meter. Okay. This is what you need to find. Now we are going to write the formula for the diffraction grating, which is d sine theta equals n lambda. Just put in the values. D sine 28.2 equals 1 into lambda. This is 380 into 10 raised to the minus 9. Okay, this is just 1. And from here, you have the value of d to be equals to 803 into 10 raised to the power minus 9 meters. Now d is actually equals to 1 over n, but here n is equals to g. So we are going to have 1 over g is equals to 803 to 10 raised to the power minus 9. And from here, you have the value of g to be equals to 1.2 into 10 raised to the power 6 per meter. Okay. 3.5. A scientist wants to obtain an accurate value for the difference in wavelength between line X and line Y. Okay. She has two options. Option 1, to analyze the second order spectrum from the original grating, and option 2, to analyze the first order spectrum for the grating with 2G lines per meter. Very important to understand. Here you have either n equals 2 and same number of lines, okay? Or you have first order and double number of lines per meter. So this is the option. And which one we need to choose? We have to see. So first of all, option 1. What about option 1? If we use option 1, Then what we need to write? We need to write G, which is the number of lines per meter. It is actually same as before, as they have mentioned, original. And we need to use the second order, not the first order. Okay. So for that, we will just write d sine theta equals n lambda. Okay. And from here, we need to find d sine theta equals 1 over g. And this will be equals to 2 lambda. All right. Because n is equals to 2. And sine theta is actually equals to 2g lambda. All right. This is for option 1. And what about option 2? So sine theta means the separation between line X and line Y, or the fringes of the first order and the second order. So option 2, you have the first order, but the number of lines like on the gratings per meter is double. So you have to write again d sine theta equals n lambda. You will just put here 2g sine theta equals n lambda, and n is actually equals to 1. Okay, so from here, sine theta is going to be again 2g lambda. So you can see that there is no specific information we are getting in terms of angular separation. So you will write angular separation is same in both cases. So no information obtained from this. But if we use option 2, sorry, if we use option 1, so what will happen? In option 1, however, we are going to write, however, in option 1, we have second order fringes or the images, okay? Second order, and second order is actually dimmer. Shows dimmer image, right? Not good. So it is also possible that the images are like overlapped with each other, because you are talking about the second one, you are going far away. So the images are already blur or faint or dim, because the first one is always the sharp one, then the second, third, fourth, fifth are keep on getting fainted because the energy is getting reduced. So you can say in option 1, we have second order or dimmer image, so not good to distinguish X and Y, because it is already faint or dim. So how will it be able to clearly distinguish X and Y, which are very close to each other? But in option 2, we have double lines and first order. So because of that, what will happen? The first order will be very, very bright, and the others can be little, because y is very close to x. So x will be very, very bright, while the y is little dim. And this can be helpful to identify x and y, as mentioned in the question. Okay. So it for distinguishing x and y. And so to calculate the difference of the wavelength. To calculate the difference of the wavelength between X and Y. Okay. 4. The deuterium tritium DT reaction is a nuclear reaction between two isotopes, okay, of hydrogen. The DT reaction is this. The energy from this reaction is transferred to the kinetic energy of the helium nucleus and the kinetic energy of the neutron. Assume that the kinetic energy of the hydrogen nuclei are zero just before the reaction occurs. Okay, very, very important to understand. The energy, kinetic energy here is zero before reaction happens. Okay, and after the reaction happens, the kinetic energy is not zero, and they're moving in opposite directions just to conserve the momentum. Okay, because here momentum is also zero because they are at rest, so kinetic energy is zero, but momentum is also zero, and after that they are moving. They have some kind of non-zero kinetic energy. Assume that the kinetic energies of the hydrogen nuclei, I mean their fusion is giving them the kinetic energy, okay, which was actually zero before. Kinetic energy of the hydrogen nuclei was zero before the interaction, and after the fusion they have banged each other and turned out of two into one. That is fusion. So where two nuclei turn into one nuclei, that is fusion. And when they turn into one, they created helium and neutron, and both now having kinetic energy. So they are now asking us, show that the kinetic energy of the neutron represents approximately 80% of the total energy transfer. So it's quite easy to understand that the kinetic energy is actually equals to half mv square, right? And I need to play a trick here. Just multiply mass and divide mass, convert it into momentum, right? So we will write p square over m. So that will turn into p square by 2m. Now, here is a point of understanding. You can see in this interaction that the momentum is conserved because both are moving in opposite direction. So you will just write constant over 2m. All right. So from here, I'm going to understand that the kinetic energy is that inversely to mass. So what does that mean? The total energy is like 4 and 1. So how much is the mass? Mass is like 4 here, and here it is 1. So total mass is like 5. Okay. So as we will say, mass of He4 is 4 times of mass of neutron. So we will say the total number of particles here are 5. Okay, so 5 are having 100% of the kinetic energy, and since mass is inversely to kinetic energy, so we will say, so out of 5, 1/5 of Ke belongs to helium, and 4/5 belongs to neutron. How? Because mass is inversely to kinetic energy. So helium is 4 times heavier than neutron, so neutron should have 4 times more energy than helium. So therefore, I will say 80%. So 4 parts out of 5 means 80% of total Ke belongs to neutron. Okay, the combined kinetic energy of helium nucleus and the neutron is 2.82 times 10 to the power minus 12. Calculate the initial speed of neutron. Okay, so for this question we will just write kinetic energy equals 2.82 into 10 raised to the power minus 12 joules. Okay. So it is the total energy, total kinetic energy of neutron and the helium. But we know that they're talking about the kinetic energy of neutron. So kinetic energy of neutron was 80% of this total. Since neutrons Ke is 80% of total Ke. So we will just do Ke of neutron equals 0.80 times 2.82 times 10 raised to the power minus 12, which is equals to 2.25 into 10 raised to the power minus 12 joules. Okay, now it's very easy to do. Half mv square equals 2.25 into 10 raised to the power minus 12. Okay, and from here we know that the mass of the neutron given in your formula sheet is 1.67. That too will come up here, and the mass of the neutron will go there down to 10 raised to the power minus 27. So that is the mass of the neutron. And take the square root on both sides, and final answer is 5.19 into 10 raised to the power minus 7 meter per second. Question number 5. A cable system is to be used to transfer supplies across a river. A model of the proposed system is built in order to test its performance. The model consists of a cable attached to two vertical posts A and B as shown in the figure. A pulley P of negligible mass is attached to the cable. In this question, the length of the cable does not change and the weight of the cable can be ignored. Okay, so there is no extension and there is no friction. An object O is attached to P. In one test, O and P are at rest in the position shown. The weight O is 350 Newton. Figure shows figure 4 is a force diagram drawn to scale. It means you have to measure the angles using your protractor. Okay, using your D, you have to calculate the angles because it is drawn to scale. It represents the magnitude of the direction of the tensions T1 and T2 in cable when O is at rest in the position shown in the figure. At this position, resistive forces are zero. Complete the force diagram and go on to determine using your diagram the magnitude of T1 and T2. Okay, so please do that using your protractor. I will just do it for your understanding. So one component is this, and the one component is this. Using your D, you have to calculate these angles. Okay. So you have to do that as well. Now you can see that this is the angle and this is the angle. And when I saw that in the masking, this angle was given to be 34 degrees and this was given as 12 degrees. Okay, because I cannot draw it to the scale. I don't have paper. Therefore, you have to do it on your own and check if the answer is correct or not. And the W is acting downward from here. So from here, I can get two of the equations. This is T2 cos 12. This is T1 cos 34. This is T1 sine 34. And this is T2 sine 12. Okay. If you don't know how did I get cos and sine, so you need to remember the place or the side where you have 90 degree and the angle is always cos. So you have this angle and this 90 here, so it is always cos, and the other side is sine, and of course this one is your resultant. T1 and T2 is your resultant. Now from here you can make two equations. One is rightward forces are equals to leftward forces. So what is rightward force? T2 cos 12. And what is leftward force? T1 cos 34, right? And when I calculate the answers, I get T2 from here to be equals to 0.8441. Okay. Now, the second one that I can get from here, upward forces are equal to downward forces. Now, what is the upward force? Upward force is one, this one, and the other one is this one. So we will say T1 sine 34 plus T2 sine 12 equals W. And W is 350. Okay, so T1 sine 34 plus T2 sine 12 is 350, right? Upon simplifying, I am getting to a point 0.560 T1 plus 0.175, not 175, my apologies. Okay, so just need to put in the value 0.560 T1 plus T2 is actually 0.844 T1. I'm just putting it sine 12 equals 350. Okay, and when I simplify that all, I'm going to get 0.560 T1 plus 0.175 T1 equals 350. All right, so this is T1. So from here, T1 is 476 Newton, and just put that back here to get T2. So T2 is 0.844 T1, and T2 is 0.844 into 476. So T2 is 401 Newton. Okay. 5.2. In a second test, pulley P with O attached is released from A. So you're releasing it from A. And where is A? Make sure that it is on the top. So you're releasing it from here. And it is reaching here. Okay. Okay. So the change in height of the center of the mass of O between A and B is 4.5. It's very easy to understand now. This is the height by which the body came down from A to B. Okay. The distance traveled along the cables is 18 meters. Now the total cable from A to B, it's like a slant distance or a slant height, not the vertical, but the slant height. Like the inclined distance that body covered from A to B, it's 18. Okay. And the speed of O when it reaches B, this is your final speed. Okay. And initially it was started from rest, so it should have a zero initial speed, right? And calculate the average resistive force on O and P as they move from A to B. It's a 5 marker, okay? So first of all, you have to draw a vector diagram. So this was your A, this was your B. And OP moved from here to here and covered a distance of 18 meter. And while doing so, it traveled 4.5 down there because the center of mass of O means the weight actually moved from here to here. So that is actually your 4.5 height. Okay. So that is your diagram. And while doing it, like for example, like doing it, the weight was acting downward and there was a normal. Okay. And the components of weight are these ones. Okay. So from here, I'm going to get, if this is my theta, this is W cos theta, and this is W sine theta, okay? And this is W, correct? So N is balanced with W cos theta, and W sine theta is the one that is taking the body down, All right. Now let's take the pen red again. Okay. So. Now I will simply say whenever you have the question in which body is coming down through an inclined plane, it means that you have to consider changes in the gravitational potential energy and the kinetic energy. This is the most easiest approach you can have. So I will do the same. Change in gravitational potential energy is equals to change in kinetic energy. Okay? So when I do that, I say the mgh is actually vertical height. Mgh equals half mv square. Correct? So let me calculate the change in GPE first. Equals mgh equals what is the mass of the object? It is going to be 350 newtons divided by 9.8. This is m, g is 9.8, and h is 4.5. So this is 1575 joules. That is the total gravitational potential energy it has lost while moving from A to B. Okay. Then what is the change in kinetic energy? The change in kinetic energy is half mv square, and again half m is 350 divided by 9.8 into what is the speed? Speed is 18, so you're taking the square. Okay, and when you're taking the square, it is going to be 754 joules. Now you see, out of 1575, which was the total energy lost, how much was used in moving the body from A to B? That is kinetic energy. So how much is lost in friction? Of course, lost in friction. You understand my point? From A to B, you lost the gravitational potential energy of 1575 joules. But the energy that actually take the body from A to B in the form of kinetic energy is only 754 joules. So lost in friction is actually 1575, which was total initially lost. And this one used to take the body down to B. So this is your lost energy. All right. Now they asked us to calculate the force, the frictional force. So this is the amount of work that we have lost as. So we are now simply saying friction force work done is equals to friction force into distance. So what is the friction? What is the amount of energy lost due to friction? This is our friction force, and this is the distance. So simply we are going to divide them, and we are going to get the answer for the friction as 45.6 Newton, which is rounded off to 46 newtons. I hope you understand that. 5.3. O contains a fragile item packed in suitable material. Explain how the material can prevent damage to the fragile items when O stops suddenly. Okay, this is also a question. So here, please hold on. Okay, so here I will say there are so many ways to answer this question, but I will answer in this way. As we know that F is equals to MA, okay, F is equals to MA, and from here F is equals to V minus U over T. So if I open up the brackets, it will be MV minus MU over T, which turns into M into V as final momentum minus M into U as initial momentum over T. So I can write that change in momentum is as delta P and change in time as delta T. So this is my formula. Now from here, I can see that here delta T is stopping time. Okay. And if I increase the stopping time, if stopping time delta T is increased, then the force impact on fragile will be small. Impact on fragile object will become smaller. All right. So I believe this is quite enough to understand the answer, as F is inversely to delta T. 6. The circuit in figure 5 is used as part of temperature sensor. The battery has an EMF of 6.5 volt and negligible internal resistance. The initial temperature of the thermistor is 22 degrees. At this temperature, the resistance of the thermistor is 350. This is the resistance. And the circuit current is 12 amps. All right, milliamps. So 12 minus 3 amps. Calculate the resistance of the variable resistor. So this is 6.5 volts. And according to Kirchhoff's voltage law, you know that the voltage here and the voltage here is actually equals to same. So 6.5 is equal to V1 plus V2. This is like the voltage supplied is equals to voltage consumed. All right. This is what the easiest form of Kirchhoff's voltage law. Now, because everything is connected in series, so current is same everywhere. First of all, I will calculate V1. So V1 is actually IR. So I is 1.2, sorry, 12 into 10 raised to the power minus 3 times R, which is 350. And when I do that, I get the answer for this as 4.2 volts. Now, according to Kirchhoff's voltage law, I say 6.5 is equals to V1 plus V2. So 6.5 is equals to 4.2 plus V2, which is the variable resistance voltage. This is what we need to find actually. 6.5 minus 4.2 is equals to V2, right? So answer from here is going to be, just subtract them and you will get the answer as 2.3 volts. Okay. Oh, not the voltage, my apology. It's actually the resistance. Once you have the voltage, which is 2.3 volts, you have to do V equals IR. Okay. So V2 is 2.3, I is 12 into 10 raised to the power minus 3 into R. So from here, R is equals to 191.67 ohms. All right. 6.2. The resistance R of the thermistor at temperature theta in K is given by this, where R naught is the resistance at the initial temperature I naught theta 0. And what is the initial temperature? 22 degrees Celsius. And B is a constant. The temperature of the thermistor is increased to 308 K. So it means this temperature is not 22 degrees. This is now 295 kelvins, because you have to add 273 in it, so it will become 295 Kelvin. This is your initial temperature. The variable resistor is adjusted so that the circuit current is again 12 milliamps. The potential difference across the thermistor is now 3.2 volts. Okay. Determine B. State an appropriate unit for your answer. Okay. So I'm going to write R equals R naught E B 1 over theta minus 1 over theta naught. Okay. That is the formula given in the question. Okay. So since R naught is the initial resistance, and the initial resistance was 191.67 that we have just calculated. Okay, for the same circuit, for the variable resistor. Okay, as you can see that Okay. So the resistance of the thermistor is 350 ohms, right? So we have to see this. So resistance, it's not 191, it's 350. Okay, it's 350 ohms because it is for thermistor, not for the variable resistance. Okay, and the thermistor resistance is raised to 318. And the potential difference across the thermistor is 3.2. It's absolutely the same, and the voltage is also same. Now you need to find the constant B. So first of all, what is R naught? R naught is 350, and what is R? R is what is R? We need to find, because 3.2 divided by 12. Yeah. So R naught is 350 ohms, and for R we have V equals 3.2 volts and I equals 12 into 10 raised to the power minus 3 amps. So V equals IR, and from here I is 3.2 divided by 12 into 10 raised to the power minus 3 equals 266.67 ohms. Okay, so I have the value of R. I have the value of R naught. I have initial temperature as 295 K. I have final temperature as 318 K. So it's all okay to go on from here. R is 266.67 equals R naught is 350. EB is this 1 over 318. My apology, because the new temperature is 318. And the old temperature is 295. And I don't have the calculator, so let's do 266 divided by 350. Oh, no. 266 divided by 350. So 0.76. Okay, so 0.76 is equals to EB, and the answer to this you can do through your calculation, through your calculator, is 2.45 minus 2.45 into 10 raised to the power minus 4. Okay, now we will take the ln on both sides. Let's see what is the ln on both sides. It's scientific, so ln of 0.76, its ln is minus 0.27. Okay, it's minus 0.27 equals the other side, ln of E. I'm just taking the ln on both sides, first of all, here and here. Okay, so the ln of here is this, and the answer to this is B into 2.45 into 10 raised to the power minus 4 into ln of E, which goes to 1. And the negatives on the both sides are cancelled. So just do 0.27 divided by 2.45. So it is 0.1102. Okay, so that is your answer. And now, because it's 4, so it is about 1102 kelvins. Okay. Now, how do I know that the reading for B is kelvins? Because on the left-hand side, what do you have? Ln has resistance, they are cancelled. It is the ratio because R and R naught is the ratio of the same thing, so it has no unit. And on the right, you just have the difference of the two temperatures. So it means the unit for the B should be kelvins because it is just the difference of the two temperatures. Okay, so 1102 kelvins is your answer. 6.3. Please hold on. Okay. Explain why the current in the thermistor needs to be controlled. It's quite obvious that when we change the current, change in current actually changes the temperature. Because thermistor is an electrical device which is used to control, which changes its temperature with the, I mean, its resistance changes with temperature, right? And the temperature changes with current. So change in current changes temperature, right? And what happens further when change in current happens, there is a change in temperature, and when temperature goes high, resistance goes down. And when temperature goes down, temperature goes high because it happens in negative coefficient temperature thermistors, not the positive coefficients. For positive coefficient thermistors, temperature and resistance are same. Temperature goes up, resistance goes up. But in negative coefficient thermistors, temperature goes up, resistance goes down. And usually when it is not mentioned what kind of thermistor it is quite understood, and it is like very much understood that it is negative coefficient thermistor. If not given, if not mentioned, you must assume it as negative temperature coefficient thermistor, which means temperature goes up, resistance comes down. 6.4. Explain how ammeters and voltmeters can be used in the circuit in figure 5 to demonstrate conservation of charge and the conservation of energy. Refer to the points X, Y, Z. So where's X, Y, Z? Okay, here. Simple. Find out the ammeter, take ammeter here, take ammeter here, take ammeter here, and get the current. Because they're all in series, you will see that the current everywhere is same, which shows the same electrons are flowing, the charge is same. So that shows law of conservation of charge. And what about the energy? So it means energy, you will just connect the voltmeter first of all here, and you will see what is the voltage, and then you will connect here, and you will see what is the voltage. Then you will add them together and see if their sum is coming to be equals to 6.5 or not. And if it is, it means the conservation of energy as well, because 6.5 joule of energy is coming, and the same energy is being utilized down there in the circuit. So you will say that put ammeter at X, Y, Z, and current at X shows same as current at Y and current at Z, which shows law of conservation of charge, which shows conservation of charge, COC. And then put a voltmeter between X and Y, and then you have to note voltage XY. Then put voltmeter between Y and Z, and note voltage YZ. And then both of them, you will see that voltage XY plus voltage YZ is equals to 6.5, which shows energy conservation, shows energy conservation, because 6.5 volts means 6.5 joules per unit of charge. So the energy supply is same, so it shows energy conservation. I hope you understand that. So that law of conservation of charge is actually KCL, which is based on law of conservation of charge, and law of conservation of energy is actually the basis for the Kirchhoff's voltage law. Question number 7. An experiment is done to investigate the stationary waves on string. A string of length 1.05 meter is attached between a clamp, stand, and a vibration generator. A stationary wave is formed on the string when the vibration generator frequency is 625 Hz. Figure shows the variation of displacement with distance from one end of the string at time t equals 0. At this time, all points on the string have their maximum displacement, as is one of the points on the string. The stationary wave is produced by two progressive waves traveling in opposite directions on the string. Reduce the amplitude of one of the progressive waves. Okay, so now you can see they are telling you that at this position where you are seeing everything is at its maximum distance. So what does it mean? It means you have these two waves, okay, which are traveling in opposite direction. You have these two waves and they are traveling in opposite direction, and when they combine you get a bigger wave like this. Okay, so it means if it has an amplitude of, I believe, 7, yeah, it has an amplitude of 7 mm, so it means it has a 3.5. So finally it is 7, so it means the one individual wave has an amplitude of 3.5 mm. Because after this instant, maybe it's quite possible that the waves goes like this. Okay, it's quite possible, but at this instant they are like at maximum displacement, so it means they have to overlap constructively and make a bigger amplitude, a bigger wave, because of this superposition. So one of the progressive waves is actually half of the given one, so it is 0.5 mm. Determine in meter per second the speed of one of the progressive waves. Now this is the displacement versus distance graph. Displacement versus distance graph always gives you the wavelength. And if I see for one complete wavelength, this is actually 0.7. The distance that covered during one cycle, one complete cycle, is wavelength. So this is 0.7 meters. Okay. Now what I see, I will just write V equals F lambda, and F is actually given as 625 Hertz. Lambda is 0.7 meters. V is 625 into 0.7 equals 440 meter per second. State the phase relationship between the two waves when t equals 0. When crest trough is meeting trough, they are combined, superposed to each other. Of course, there is no phase difference. So it means in phase, or a phase difference of 0 degree. Sketch on figure 7 a graph to show how the displacement of S varies with time. So now here you see that everything in this figure is at its maximum displacement, and S is one of the points on the string. So if S is at its maximum position from here, from what should it do? For example, if a point reaches its maximum point, and what it does after that, it goes down. So if S is at its maximum position, of course it has to go down from here. Now that is another question, what will be the period for this wave? So for that we need to count, right? We need to count the frequency and the period for that. So here I will just say the frequency is 625 Hertz. The period will be 1 over f, and that is actually 1 over 6.25, and it is 1.6 milliseconds. Okay, so 1.6 millisecond is somewhere, maybe 1.6 is here. Okay, so from here the wave is going down. Okay, so if 1.6 is like the time period, so it means 0.6 is something where the wave will go half of it. Okay, like that. Okay, so I will say 1.6. 1.6 divided by 4. Let me do that. And I'll see where the wave will go. Okay, please wait. 1.6 is the time period. Okay, 0.4. So the wave is going to pass through 0.4. Let me see that in the mark scheme as well. Okay. Okay. So I think it should go, just hold on. Okay, here it is, the mark scheme. I need to check, please hold on. Yeah, it is passing through 0.4. Exactly, I was correct. Okay, thank you for your patience. So from here, what actually I did in this question? They are saying make a wave diagram for the wave S. So they said at this point at t equals 0, everything is at its maximum position. So S is at its maximum position of 4. Now 1.6 is the total time period for the wave. So it means it will pass, 1/4 will pass from here. Okay, and the next quarter will pass from here up till here, because -4 will be here, so it will be here. Okay, so you will say this, and then the next quarter will be 0.8, and it will be 1.2, 1.1, 1.2. Okay, so this is 1.2. It will come here, and then from here it will come here. Okay, so this is how it will complete one cycle, and from 1.6 all the way to 2, it will come like this, 2. Okay, so this is the end of section A. So now in the second part, I will do the MCQs. Okay, please hold on and wait. Thank you.